Welcome back, everybody. We are looking at page 112 in the workbook, example 2, and this is asking us to calculate a line integral using the fundamental theorem of line integrals, but we're going to try to do this in a little bit more of a systematic way in this example. Okay, so let's read this together. They first give us a two-dimensional vector field and ask us to demonstrate that it's conservative, to then find a potential function for the vector field, and then finally to calculate a line integral. Okay, so the first part of that is asking us to show that this is a conservative vector field. Okay, well, we talked on the previous page about how to do that for a two-dimensional vector field. It came down to something that we called the curl test, and in that test we gave names to the two components of our vector field, f1 and f2, and the test told us that it's about taking partial derivatives and seeing if they have the same value. Okay, so we called that test the curl test. We're going to do that here. And the two derivatives that we need to compare, okay, you can look back on the previous page and confirm this. We need to confirm that partial f2 partial x and partial f1 partial y have the same value. Okay, so let's start with f2. Okay, so you can see above that f2, the second component in our vector field, is 3x plus 2y. What do we get if we take the derivative of that with respect to x? Well, we're going to get a 3 for the first term, and the 2y is going to go away, so we get 3. Okay, and similarly, the derivative of f1 with respect to y would look like the derivative of the first component. Notice that that's also 3. Okay, and so the fact that those two things are equal tell us from the curl test on the previous page that f is conservative. Okay, so we have cleared the first hurdle, and that calculation confirms that it's possible to find a potential function, all right, which is our next step. All right, so in calculating a potential function, all of the examples that we did up until now, we were kind of doing a guess and check approach. We're going to try to do it a little bit more systematically in this case. So remember what a potential function is again. Okay, what we want is a function little f whose gradient is equal to our vector field, okay, which I'm just going to rewrite here. Okay, so we want that statement to be true. All right, well, for that to be true, we need the first component to be equal to the derivative of little f with respect to x, and we need the second component to be the derivative with respect to y. So that gives us a starting point that looks like this. Fx is going to have to equal 3x squared plus 3y, our first component, and fy is going to be 3x plus 2y, our second component. And the question then is, how do we get from those partial derivatives back to a function? Okay, let's do the calculation in the first line first. So we want to go from the derivative of f with respect to x back to the original function, which means we need to integrate with respect to x. All right, so we're going to integrate both of those terms, and remember, this is an integral with respect to x, so we are treating y as if it's a constant. Okay, so if we integrate 3x squared, we're going to get x cubed, and 3y is just a constant, so we're just going to get 3xy when we take that derivative. Okay, but there's a term missing here. Okay, what happens when you take an indefinite integral? Okay, if you take an indefinite integral, you need a plus c on the end. Okay, but there's a little bit of a catch here. Okay, we've got two variables involved in this integral that we're taking, and we're treating y as if it's a constant. So when we add our plus c here, we have to account for the possibility that there may very well be some y's in our constant, because y is being treated as a constant. Okay, so instead of writing plus c, we're going to write plus p of y, just to acknowledge the fact that that constant that we add may very well have some y's in it. Okay, So that kind of completes our calculation on the first line. Okay, and now we'll move on to the second line. I'm going to just give us a little bit more space here. Okay, so I'm going to move the Fy down a little bit. Okay, and we're going to repeat the same idea, just integrate back to get our function, this time with respect to y, 3x plus 2y dy. And so we need an antiderivative, and this time we're treating x as a constant. So when we integrate 3x with respect to y, we're going to get 3xy, and then integrate 2y, we'll get y squared. And we're going to add a plus c, but this time our plus c may very well contain x's in it, so we'll write it as q of x. Okay, and here's the thing that's interesting about these calculations. Notice that f of xy is equal to two different things, both of these expressions. And so since both of those are equal to f of xy, these have to be equal to each other. Can't be any other way. And so to get our final potential function, what we need to ask ourselves is, what would these constants on the end have to be equal to in order that these two formulas match each other? Okay, well, let's start with the p of y. What would it have to be? Okay, we can answer that question by looking down below and asking, is there any term that you see down there that we don't already have in the top line? And one that I notice is the y squared that's sitting here. Okay, so we need to make p of y equal to y squared so that those two formulas match each other. Okay, and then moving down, q of x, what would that have to be so that the second formula can match the first formula? Do you see anything up in the first line that we don't have in the second line? And I notice one thing right here. There's an x cubed up here that's not down below. Okay, so we'll make q of x equal to x cubed. And notice that if we do that, now these two formulas really are the same as each other. We get equality, and that leads us to a final potential function that looks like x cubed plus 3xy plus y squared. That's what both of those two formulas up above are equal to with our choices of p and q. Okay, and if you like, you could maybe pause to confirm that calculation. If you take the gradient of this function f, it should agree with the vector field that we started with. Okay, and you can do that if you want, just to confirm that our potential function is correct. Okay, so we have just completed the second part of the problem, and we are ready for the third and final part, which says, can we calculate this line integral? Okay, well, the thing is, once we have a potential function, the calculation of that line integral is not too bad, because all that really matters is the starting and the ending point, the 0, 0, and the 2 pi 0. We just need to substitute those numbers in, and we should have the value of the line integral. So to finish, the line integral should be f of, okay, let me scroll up again here. Our second point is 2 pi 0. And our first point is 0, 0. We just need to substitute those numbers into the potential function above, and we should have our answer. Okay, so we're going to take 2 pi and 0 and plug those in for x and y. So 2 pi cubed plus 3 times 2 pi times 0 plus 0 squared. There is f of 2 pi and 0. Minus f of 0, 0, and notice that if you plug 0 in for x and y, you're just going to get a bunch of zeros. Okay, so that second term goes away. Okay, so what do we get for our answer here? Well, the only thing that really survives is the 2 pi cubed. We do that calculation, we're going to get 8 pi cubed. That should be the value of our integral. Okay, and we are done with the problem. Okay, I do want to make one final comment here, just as sort of an afterthought. Okay, so you might have noticed in the original statement of the problem, they gave us a path. okay, said that the path was y equals sine of x, starting at 0, 0 and ending at 2 pi 0. I just want to draw that briefly so we can visualize the line integral that we calculated. Okay, so we started here at 0, 0. Here's 2 pi 0, and the sine function kind of looks like this. Okay, so that's the curve, C, that we integrated along, and I want to emphasize again, that curve totally didn't matter in this calculation. All that mattered was the starting and the ending point. You can